So far in our discussion of energy, we've been talking about conservation of energy, which means that if we look at everything, we will see that energy is not created or destroyed. It merely changes forms. However, it's not always easy to look at absolutely everything. Sometimes we want to focus on only one object and see what's going on with that one object. Let me give you a good example. In Rio, there was weightlifting. Let's take a look at the new world record weightlift. So as we could see, we have a 250 kilogram weight that was lifted approximately 2.5 meters up into the air. So we know that that weight has gravitational energy. But where did that gravitational energy come from? Well, it came from our Georgian weightlifter. But where did it come from in him? Well, it probably came from the breakfast that he ate this morning. And the question really becomes, well, do we know how much energy he got out of the breakfast this morning? Probably not. We'd have to ask chemists how much energy he got from his breakfast this morning. But since we don't have time or maybe access to chemists right now, we instead will try to eliminate our Georgian weightlifter from our analysis, and instead we'll only focus on the 250 kilogram weight that he was lifting. When we do this, when we stop looking at absolutely everything and we look at only one object, we no longer see a conservation of energy in that object. For example, that weight, when it was on the ground, had 0 energy, and when it was up in the air, it had a huge amount of energy. So that change in energy is what we call work. So you could write this as work is equal to a change in energy. Now there's another way that we can talk about work. In order to change the energy of a system, we need to have a force causing some sort of displacement. That's the traditional definition of work. It's the definition that you'll see in textbooks. And so we can do that using the following equation. Work is equal to a force multiplied by a displacement. But that displacement can't just be in any direction. It has to either be in the same direction, the displacement has to be in the same direction of the force or in the opposite direction of the force. So to do that, we can add a nice cosine of theta, because we know that cosine of 0, which means they are in the same direction, is 1. Cosine of 180, which is opposite directions, is -1. And cosine of 90, which would be perpendicular, is 0. And that kind of demonstrates the fact that if you are going to do work on an object, your force and your displacement have to be in at least the same direction. So let's actually outline that. If your force is perhaps to the right and your displacement is to the right, then your angle ends up being 0 degrees, and the work that you do will be positive. You'll gain energy by doing that. If your force is to the right, but your displacement is to the left, well, then the angle between those two is 180 degrees. And so you still will have work done on an object, but now your work is going to be negative. So that object is going to lose energy. And then finally, if your force is to the right, and perhaps your displacement is up, well, the angle between those two is 90 degrees, and so no work will be done. Let's look at some word problems to help us with this. A 20 kilogram suitcase is raised 3 meters above a platform by a conveyor belt. How much work is done on the suitcase? So we've got, let's draw a little picture. Here's our conveyor belt. Here is our suitcase. And that suitcase is being raised up 3 meters. So we could think of this as work is a change in energy, and the energy that we're changing is gravitational energy. So we could treat this as work is equal to mg delta y. So our work is going to be 20 kilograms times 0.8 newtons per kilogram times 3 meters. And that'll give us a work of 588 joules. Let's do a second one. Upon arrival at an airport, a passenger picks up her suitcase and drags it with a 100 Newton force at a 60-degree angle for 200 meters from the airport exit to her car. How much work did she do? Now, really what she's doing when she drags this suitcase is I don't know why all these problems are suitcases, but I guess that doesn't matter. Anyway, she's really dissipating a whole bunch of energy as she walks her suitcase to her car. And it would be really hard to try to calculate how much energy is being dissipated. So let's use that second definition of work, F delta x cosine of theta. So the force that she's pulling with is 100 newtons. The delta x that she travels is 200 meters. And the angle that she's pulling it is 60 degrees. So if we type all of that into our calculator, we get that she must do 10,000 joules of work. Let's do the last one. Joe tries to push his car up a hill. He pushes with a force of 300 newtons at an angle of 30 degrees, but the car doesn't move. How much work does Joe do? Well, the key about changing energy is that you do have to actually make something move. And Joe, well, he's not making his car go anywhere. And so if he's not making his car go anywhere, well, he is doing 0 joules worth of work.